In this lesson, we are going to look at limits involving infinity, specifically limits as x approaches positive or negative infinity. In previous classes, this may have been referred to as end behavior, or what's happening at the ends of the graph, the left and right ends of the graph. And I'll just use this picture we have here as an example. We've got a picture of a rational function, y equals 8 over x minus 2, which has two asymptotes. We've got a vertical asymptote where x is 2, and we have a horizontal asymptote where y is 0. And if we consider these two questions here, what is the limit as x approaches positive or negative infinity? We want to look at the ends of the graph, or we want to look on the graph where x is approaching positive infinity way out here at the right end, or x is approaching negative infinity way out here at the left end. And if you look and think about, well, what is the graph doing there? Let's start with as x approaches positive infinity. If I put my pencil on the graph and go towards the positive infinity end of the graph, I can see that my y values are approaching the asymptote, or the y values are approaching 0, where the horizontal asymptote is. And then if I try to evaluate the limit as x approaches negative infinity, I can put my pencil on the graph and go towards the left end of the graph, where again, the graph is approaching this horizontal asymptote at y equals 0. So the y values are again approaching 0. And if you'll notice, these two y values correspond to the place where we find the horizontal asymptote. So the limit as x approaches positive infinity or x approaches negative infinity gives you a method for finding the horizontal asymptote. Oops, let's go back one. Oh, no. Okay, so in a previous class, you probably learned these shortcuts for determining where the horizontal asymptote is. Well, this also is another way of saying what is the limit as x approaches positive or negative infinity. This is specifically for rational functions. We can use it for some other functions, which I'll point out as we go through this unit. So the two rules that are going to apply to S are these first two rules. This third rule won't really apply. I'll explain in 1 minute when I get to it. In the rational function, if the power of the numerator is equal to the power of the denominator, or this means the highest power of x in the numerator is equal to the highest power of x in the denominator, then we know that the limit as x approaches positive or negative infinity is equal to the ratio of coefficients of the highest degree terms, which also means this is equal to the horizontal asymptote. I'm going to give you examples of all of these in the next slide. If the highest power of x in the numerator is less than the highest power of x in the denominator, then the limit as x approaches positive infinity of f of x equals 0. Or in this case, the horizontal asymptote is y equals 0. If the power of the numerator is greater than the power of the denominator, then the limit as x approaches positive or negative infinity is positive or negative infinity. And this is where you would wind up with a horizontal asymptote that is possibly oblique or parabolic, or some other non-linear shape. We will not see this in calculus. The only two types of non-vertical asymptotes we see are horizontal ones, like in these first two descriptions. So let's look at some examples for these. So you see I've got three limits here. So the first one, the limit as x approaches positive infinity of 3x squared minus 1000x minus 920,000 over 4x squared plus 500x plus 1 billion. It looks like there are some really, really big numbers here. But actually, when we're evaluating these limits as x approaches positive or negative infinity, we only care about the leading term, the term with the highest power of x in the numerator and the term with the highest power of x in the denominator. The reason is these other terms are going to become so small, they're going to be negligible relative to the leading term. So for example, if I plug in 1 trillion for x, a large number as x approaches positive infinity, 3 times 1 trillion squared is going to be so big that I'm not even going to notice the minus 1,000 times a trillion minus 920,000. Those aren't even going to matter. So all I care about is the leading two terms. And I can see the power of x is the same as in the numerator as it is in the denominator. And therefore, the limit as x approaches positive infinity is 3/4, which tells me that the horizontal asymptote is at y equals 3/4. In the second example, the highest power of x in the numerator is x to the 5th, and the highest power of x in the denominator is x to the 7th. The power is greater in the denominator, which means the denominator is growing much faster than the numerator. So I will be dividing a smaller number by a much larger number. And in that case, because I'm dividing by a much larger number, the limit as x approaches positive infinity of this expression will be 0, which also means that this graph will have a horizontal asymptote at y equals 0. In the final example here, I have an expression, the limit as x approaches positive infinity of 2x to the 5th minus 3x squared over 7x squared plus 4. In this example, the highest power of x in the numerator is greater than the highest power of x in the denominator. So now we're going to have a very large number in the numerator divided by a much smaller number in the denominator. And the limit of this function is going to be positive infinity. Now, that doesn't directly tell me where the horizontal asymptote is. I would need to do further explanation if I wanted to graph this function and show the horizontal asymptote. I would have to do the long division implied by the problem to find that asymptote. Now, again, we are not going to have any of this third type of problem in calculus in terms of finding the asymptote. You may be asked to evaluate the limit, but you wouldn't be asked to find the non-vertical asymptote. Oh, I should say, I should correct this. This would not be a horizontal asymptote. This would be a non-vertical asymptote, either oblique or some other non-linear type. Okay, so now I want to look at just some basic rules looking at calculations involving infinity. So I've got a graph of y equals 1 over x, the standard inverse variation function, which has a vertical asymptote at x is 0, because when x is 0, the denominator is undefined, and a horizontal asymptote at y is 0, which we could have figured out using the rule I just gave you. Okay, now let's start in the middle of the graph here. The limit as x approaches negative infinity. So I can look at the graph and I can see what y is approaching as I approach negative infinity. I can look and see that the y values are getting closer and closer to that horizontal asymptote, and so y is getting closer to 0. Mathematically, I could show that by showing, well, let's look at some values. If I plug in a big negative number, let's say I plug in -10, I'm going to get 0.1. If I divide by -100, I get -0.01. And if I divide by, let x be -1,000, I get 0.001. And you can see that your y values are getting smaller and smaller and smaller, closer and closer to 0. Similarly, over here on the right side, as x is approaching positive infinity, if I divide by big positive x values, I'm going to get the corresponding positive values. If I divide by 100, I get 0.01. If I divide by 1,000, I get 0.001. And so you can see, again, the y values are approaching 0. So from these two limits, I want to make a generalization. I'm going to draw the conclusion that the limit as x approaches positive or negative infinity of a constant, in this case our constant was 1, over x, if I divide a constant by an infinitely large number, I'm going to get 0. Okay, over here on the left, let's look at these other three limits. All right, the limit as x approaches 0 from the left, which means that's over here on the graph, the left side of 0. You can see the graph is pointing down. Okay, so what's happening? So if I plug in a really small negative number, 1 divided by 0.1, I get, negative number, so -0.1. That's going to give me -10, right? 1 divided by -0.01. That's going to give me -100. The smaller my x value, the larger my result will be. So as x gets smaller and smaller and smaller and smaller in the negative direction, my y value, or the value of this limit, is approaching negative infinity. And then similarly, if I divide by infinitely small positive numbers, the result will be infinitely large positive numbers, right? So the limit as x approaches positive infinity, the limit as x approaches 0 from the right, that's over here on the right side of the graph, is positive infinity, and you can see the graph is going up towards positive infinity, and on the bottom going down towards negative infinity. Well, if the limit as x approaches 0 from the left is negative infinity, and the limit as x approaches 0 from the right is positive infinity, then it must be true that the limit as x approaches 0 does not exist, and that is because the left and right-hand limits are not equal. The left-hand limit is negative infinity, the right-hand limit is positive infinity, therefore the limit does not exist. So there is no need for you to memorize the rules we just discussed. I'm going to explain a way using limits to evaluate the limit as x approaches positive or negative infinity without needing to memorize those rules that you learned in a previous class. So anytime you see a limit as x approaches positive infinity of a rational function, you are going to divide each term by the highest power of x in the denominator first. And then you can just apply the limit rules that we just went over, and you will naturally get the correct answer without needing to memorize any rules. So I have some examples here. I'm not even going to think about what type of limit this is. I'm just going to follow the process that I just explained. Let me also first say that if it is not explicitly stated, it is understood that when you see the limit as x approaches infinity, it means positive infinity. If they mean negative infinity, they will put a negative sign. You are expected to explicitly state positive or negative infinity in your answer. All right, so I'm going to evaluate this limit. It is a rational function, meaning the numerator and denominator are both polynomials. So I'm going to divide by the highest power of x in the denominator, which is x to the first. I'm actually going to write this division as a multiplication because I'm dividing by x to the first, which is the same thing as multiplying by 1 over x. If I multiply by 1 over x over 1 over x, then I'm really just multiplying by 1. I'm not changing this expression. So I have the limit as x approaches positive infinity of, well, x divided by x is 1. And then in the denominator, I have x divided by x and plus 3 divided by x. Oops, sorry. X divided by x should be a 1 plus 3 divided by x. And now I'm actually ready to evaluate the limit. When I plug in infinity, I get 1 over 1 plus 3 over infinity. And we just discussed in the previous, in the limit rules I just discussed, that anytime you have a constant divided by infinity, that equals 0. So I have 1 over 1 plus 0, which is 1. That also tells me that if I were to try and graph this, my horizontal asymptote would be at y equals 1. Okay, second problem here. The limit as x approaches positive infinity of 2x squared minus x plus 3 over 3x squared plus 5. The highest power of x in the denominator is x squared, so I'm going to divide each term by x squared. Okay, and I get the limit as x approaches positive infinity of 2x squared over x squared is 2, minus x over x squared is 1 over x, okay? And then, because I can cancel an x there, and then plus 3 divided by x squared. And then in the denominator, I'm going to get 3 plus 5 over x squared. So now you can see that I have a 2, and when I actually evaluate this limit, this 1 divided by infinity, 3 divided by infinity squared, and 5 divided by infinity squared, those are all going to equal 0. So that means I'm going to wind up with 2 minus 0 plus 0 over 3 plus 0, or 2/3. And again, if I were graphing this, I would have a horizontal asymptote at y equals 2/3. Okay, finally in this third one, I have the limit as x approaches positive infinity of 5x plus 3 over 2x squared minus 1. The highest power of x in the denominator is x squared. So I'm going to multiply everything by 1 over x squared, which is another way of saying I'm going to divide everything by x squared, which is going to give me the limit as x approaches positive infinity of 5 over x plus 3 over x squared divided by 2 minus 1 over x squared. Well, that's going to give me 0 plus 0, that's a constant divided by infinity in both of those terms, over 2 minus 0, or 0 over 2, which is 0. Again, we're not being asked to graph these, but if you were, the graph of this function would have a horizontal asymptote at y equals 0. Okay, we just have a couple more here. I might ask you to pause the video and do these 3 on your own, and then come back and check your answers. All right, so for the first one, I'm going to divide everything by x. The highest power of x in the denominator is x to the first, and I get the limit as x approaches, again, that's going to be a positive infinity if it's not explicitly stated. And I'm going to get 2x minus 3 over x divided by 7 plus 4 over x. Well, now when I evaluate this, I'm going to get 2 times infinity minus 0 over 7 plus 0. Well, 2 times infinity is just infinity. And when you divide infinity by 7, you still have an infinitely large number. So my answer here is positive infinity. On the next problem, I'm dividing by x squared. Again, the highest power of x in the denominator is x squared. Notice in this problem, x is approaching negative infinity. So when I divide by x squared, I get the limit as x approaches negative infinity of 4x minus 7 divided by x over 5 plus 11 over, 11 over x squared. So again, we have 4 times positive infinity minus 0 over 5 plus 0. A situation just like the last one, and I'm going to get positive infinity. Oh, sorry, I've made a mistake here. We are approaching negative infinity, so let me correct that. I'm going to have 4 times negative infinity minus 0 divided by 5, which is going to leave me negative infinity divided by 5, which is still negative infinity, and I have another mistake there. My answer should be negative infinity. All right, in the last one, the highest power of x in the denominator is 3. Again, I have a problem where x is approaching negative infinity, so I'm going to multiply everything by 1 over x cubed. The highest power of x in the denominator is x cubed. So I have the limit as x approaches negative infinity of 8x squared minus 1 over x cubed. And then I have 9 plus 7 over x plus 3 over x squared. So now when I plug in, I'm going to get 8 times negative infinity squared minus 0 over 9 plus 0 plus 0. Well, when I square my negative infinity, that is going to give me a positive infinity. And so my answer here is positive infinity, even though x is approaching negative infinity. And if you look at the original equation, remember I talked about we only need to concern ourselves with the leading term in the numerator and the leading term in the denominator. If x is approaching negative infinity, then x to the 5th is going to give you a very large negative number in the numerator. And then x cubed is going to give you a very large negative number in the denominator, and that fraction, the result will be positive. Hence, the limit equals positive infinity. You would not be asked to find the horizontal asymptote in a calculus class in these three situations.